Welcome to the second video under the topic of phasors. In this video, we will be deriving the phasor formula of different components of a circuit. The first component being resistor. A resistor is a passive two-terminal electrical coupe which reduces current flow. We are using two different domains, namely the time domain and the frequency domain. The major difference between both of them is their representation of current. Namely, in this figure you can easily understand that current is being denoted by small I, while in the second one, the frequency domain, the current is being denominated by capital I. Now moving towards the derivation. Here, both voltage and current are in terms of t, hence they are in time domain. Next, we are changing the time domain voltage into frequency The main reason why we are changing this voltage into the different form or called the complex form is that this alternative form allows us to relate both current and voltage associated with any element using a simple algebraic expression, which can be evaluated as this. Now, how we got this can be easily described using the Euler identity, and the same can be done with the current, hence representing it in the form of cos and sine. Thus, replacing the values of Vt and It to this form, hence we are getting in this form. Now, since we only need to find the angle related with both voltage and current, there is no need of omega and t. Hence, we are removing both from both sides. Now, changing it into polar form, it can be expressed as Vm into angle theta is equal to R into Im angle theta. Both theta here represents the angle which both form with the origin or the x-axis, which can be simply expressed as V is equal to Ri if both angles are 0. Now, we'll be taking a simple question based on what we have just studied below. Here, we are giving the voltage which is in frequency domain and resistance, and we have to find the current which is also being asked in frequency domain. But we'll find it in phasor form. The voltage can be simply written in the form of phasor by taking in consideration of what is value here and the angle being formed here. Then the voltage V can be simply expressed as 8 angle minus 50. And now we have to just find current, which is I. I can be found in polar form as V upon R, in which V is in polar form with this angle and R is as it is. Then, since there is no angle with resistance, then we can simply divide the values except for the angle, hence getting the value as 2 angle minus 50. While as if we wanted to find it in time domain, it can be simply done by using the simple formula, which is I in time domain is equal to V, which is also in time domain, divided by R, which can be simply 8 cos 100t minus 50 degree divided by 4, which is 2 cos 100t minus 50 degree. The next element of a circuit which we will be deriving is an inductor, which is a two-terminal passive electrical coupe that stores energy in a magnetic field when electric current is flown through it. The same way the time domain and frequency domain are being described in here. Now, moving towards the relationship between the voltage and the inductance of an inductor, which is being shown here. Now we are again substituting the voltage by the complex voltage, which is Vm e raised to power j bracket omega t plus theta, and L into d by dt into complex current, which is Im e raised to power j bracket omega t plus theta. Then we are finding the derivative of the current, thus getting this equation. Then again, since we don't need omega t in this equation, we are removing it from both sides, hence getting this equation, and then converting this form into phasor form and getting this equation. We get this equation when considering both the angles of Vm and Im to be equal to 0. Then this equation can be easily found. Now we will be using the just learned formula, which is V is equals to J omega L into I into this question. Here we are given voltage, which is in phasor form, omega and L, and we need to find the phasor current and the time domain current. The phasor current can be simply represented by this expression, while the time domain current can be expressed by this expression. We'll be just using this formula to find the phasor current, and that can be done by this. Now replacing the values of V, J, omega and L, we get this. One thing to keep in mind is J can be represented in phasor form as angle 90, while minus J or 1 upon J can be expressed as angle minus 90 degree. We will be using the 1 upon J form in this part, and we'll be getting the part can be a simple division, and we'll get something like this. Now since 1 upon J is pretty much same with minus J, I can write this in the form of minus J into 0.02 into angle minus 50 degree. And now we'll replace minus J with its phasor form value, which is 0.02 into angle minus 90 into angle minus 50. Now in phasor forms, angles when multiplied with each other are actually added, while when divided with each other are actually subtracted. Since we are multiplying with the two angles, hence they will be added up, and we'll get the answer as 0.02 into angle minus 140. This will be the current in phasor form, with the angle of current being 1 minus 40. And now we'll try to find the time domain current, which is IT, from the current we just found in phasor form. We'll just require three things from the complete question, which is the magnitude of current, the angle, and the frequency or omega. Since time domain current can be written as I naught cos omega t plus theta. Now, as we know the value of I naught to be 0.02, the value of omega to be 100, and the value of theta to be minus 140, then the time domain current can be simply expressed as 0.02 cos 100t minus 140, and this will be the time domain current. Now coming to the third element of a circuit, which is the capacitor. It can be described as a device that stores an electrical charge consisting of one or more pairs of conductors separated by an insulator. Here, we are representing capacitor in terms of time domain as I is equal to C dV by dt, which can be simply expressed in frequency domain as I is equal to j omega c into V. How we got to this part can be simply done by changing the current and voltage both in their complex form and then differentiating the voltage and hence getting this form. Now what we have here is a simple comparison between the time domain of different elements and that of frequency domain expressions of different elements. Like, for example, resistance is expressed in time domain as V is equal to Ri, and it is same expressed in frequency domain as V is equal to Ri, but only the symbol of current changes from small I to capital I. For inductance, the formula in time domain is V is equal to L di by dt, while in frequency domain is V is equal to j omega L into I. In case of capacitor, the formula in time domain is V is equal to 1 by C integration of I into dt, while that in frequency domain is V is equal to 1 upon j omega C into I. That's it for this video.